Hey, hello guys, welcome, vanakkam, vandanam, namaskaram. Today we are going to see another amazing video from electrostatics, which is part 2. Okay, so last time we have seen around for 40 minutes or around 1 hour, right? So today we are going to start or we are going to proceed with Coulomb's law. So as usual, we'll be completing 5 pages. So that means starting from Coulomb's law and then it will be ending in densities, okay? In charge densities, it will be ending at, okay? So first, what is Coulomb's law? See, Coulomb's law is just similar to the force, like the gravitational law that we have studied in the last year, right? In 11th and also in class 9th itself, we have studied about the gravitational law, where product of masses is directly proportional to force, and also it's the distance square is inversely proportional to the force, right? So exactly like that, when you are having two charges, which is q1 and q2, okay, if they are positive charges, that means if they both are similar charges, which means these two charges are having positive positive, or if they both are having negative negative, in that case there will be a repulsion force, okay. So that force, to calculate that force, we will be using this formula, and also for attraction force also the same formula is what used. When it is positive here, when it is negative there, automatically it becomes the attractive force, and automatically there will be some force, right? Actually, no matter what, whether it is repulsion or whether it is attraction, no matter what, there will be some sort of force. So to calculate that force, we are using this Coulomb's law. Okay, so here what we are saying is that this force is directly proportional to product of their charges. That means if the product of their charges are very high, if you multiply q1's magnitude charge and q2 magnitude charge, then automatically their resultant value will be higher, right? Because q1's value is higher and also q2 value is also higher. Okay, so that is what force is directly proportional to product of their charges. Here, I would like to say one thing, that is, see, if in case it's an attractive force, okay. Okay, if the force is attractive force, then what does it mean? That means either one of them is positive and then one of them must be negative, right? This is how they have to be. Either one of them has to be positive and another one of them has to be negative. So, which means that, so I can say that, so just now we'll be multiplying them. Force is equal to, this formula is what we are going to see, but I'm just saying force is directly proportional to q1 and q2, right? Multiplication. So this is q1 and then this is q2. Okay, so now we are multiplying them. So here q1 is going to be positive and q2 is actually here negative. So that means for q1 I'm going to put positive q1, okay, and for q2 I can put here negative q2. Okay, now let us, yeah, so force at last here, positive into negative will be negative only, right? So directly proportional to negative of q1 into q2. So that means for an attractive force, always its value, okay, the total vector quantity, the direction, it can be actually negative because of the direction, not here because of the charge, here it is negative. So for force, if it is an attractive force, then automatically the product of q1 and q2 will be negative only. This is something that you have to know. And also, for the repulsion force. Repulsive force. So for repulsive force, how it is going to be? See, it is either going to be positive and positive, or negative and negative, right? So now if I am multiplying here, so force is directly proportional to q1, which is positive, and then also plus q2, which is also positive. Okay, this is one case. For this case, I can take this as, okay, let us take this as, let us assume this as first case. So for the second case, how it is going to be? Force is directly proportional to minus q1 into minus q2, right? So minus q1 into minus q2. Okay, pata. So force is directly proportional to q1 into q2 here. And here also, see, it's going to be positive because negative into negative, it will be positive, right? So force is directly proportional to q1 into q2. So you got it. Okay, So if I want to explain some other thing, I will explain here itself. What's there in it? Okay. Oh, it's raining outside. I like rain. No, it's not raining. Okay, so somehow next, the force is actually inversely proportional to square of the distance. See, for an example, this is q1 and this is q2. Then automatically there will be some distance between them, right? So this is what the distance is. So from here to here, there will be some sort of distance, right? So that distance, let us consider that this distance is r. Okay. So if this distance is high, if this distance is automatically high, then that means what? That means this force will be very less. If the distance between these two charges is very high, that means one charge is here and another charge is over here. So which means that the repulsion force or the attraction force will be very less. But when you are bringing them closer and closer and closer, the repulsion force or the attraction force will be very high. So that is what this law says. And also this particular proportionality symbol is there, right? That means this particular proportionality relation, that is force is inversely proportional to the square of the radius. This proportionality is also known as inverse law. Okay, this proportionality is also known as inverse law. So that is why Coulomb's law is also known as Coulomb's inverse law also they will be saying. Okay, so since here is also a proportionality, here is also proportionality, now you can combine them. When you are combining them, that means force is proportional to Q1 and Q2 divided by R square. Okay, so in order to remove the proportionality symbol, so what will we be doing? Okay, so what will we be doing? So yeah, so it is actually is equal to k into q1 q2 whole divided by r square. So for removing proportionality symbol, automatically we have to input equal to symbol and a constant. That is what I have given here. So this is what the final formula is. Okay, so here k is a constant, just like how we had in the gravitational unit, right? Like that, here k is actually a constant, where k is equal to 1 by 4 pi epsilon naught. You know most of it. You know pi, which is 3.14, or which is actually 22 by 7. So here it is actually 4 by epsilon naught. So what is epsilon naught? You know 4 is a constant. Pi is also a constant. Then what about epsilon naught? We will be seeing what is epsilon naught in the next slide of this total video. Okay, so this total k value, if you're taking k value, it depends. Actually, it depends. K value depends upon the material. For an example, if these two charges are kept, in air, then the k value will be, see this one, 9 into 10 to the power of 9. If they both are kept in air, if they both are kept in water, then that differs. When they are being kept in metal, that differs. When they are being kept in oil, then that differs. Okay, but most probably for us, they will be giving only air. Okay, not most probably till now, for those sums which I have seen, I haven't practiced those many sums, but some sums I have practiced, right? So in that, everywhere we had to use only this value. Okay, they will not give you other than this value, but if they give also for the safety purpose, I'll be saying those values also. Okay, so here that means you can also, if you are putting this k value over here, which means this will be a final force formula, which is q1 q2 whole divided by 4 pi r square. Yeah, 4 pi epsilon naught r square also you can take. So from this you can, yeah, that's it, very simple. It's right, very easy, right? Okay. So now what is epsilon naught? That's a question which most of you guys will be having, because we haven't seen what is epsilon naught is. Perfect. Okay. So what is epsilon naught? See, oh, not this light, this one. So epsilon naught is actually known as the permittivity. Epsilon naught is known as permittivity. See, exactly like epsilon naught will be studying about mu naught. Okay, we'll be also studying about mu naught, but epsilon naught is studied in this electrostatics, but mu naught will be studied in electrodynamics. Okay, which is actually complete opposite of electrostatics. Electrostatics means charges are in rest. Electrodynamics means charges are in motion. That's what the difference is. Okay, so epsilon naught is the permittivity. What is the permittivity? Very simple. For everything in this world, for an example, I'll be taking this note. Okay, so this note I have taken. So this note, towards this note, if you are passing electric field, this note has the capacity to pass electric fields throughout it. If you are passing, it will be going like this and it will be coming out, but there will be some sort of resistance, so for this electric field to pass. So that particular resistance is what is said as the ability to pass. Okay, it will be having some ability to pass, right, that electric field towards it. So that particular ability is what known as permittivity. So epsilon naught means it is in air. Not when wherever you are putting not na, either it means it is in air or it means that it is in the standard condition. So here it means in air. So exactly if in case for air alone we'll be using epsilon naught because that is what we use for most of the sums. So they have given a separate symbol for air itself, and the value is going to be for epsilon naught, which is 8.854 into 10 to the power of minus 12 coulomb square meter minus 2 and Newton inverse. Okay, but whenever the ability differs, for an example, I have said this note now. For this note, we will not be representing it with epsilon naught. For air only, we will be representing it with epsilon naught. But for medium, see, this note is a medium. Oil is a medium. Water is a medium. Okay, any other density. Okay, the substance which density is not equal to air. Okay, so for those substances, we will be using just epsilon. Okay, just epsilon in sense it will be just like this. Okay, or in few textbooks you will be also able to see m. Okay, epsilon m like that also you can see. So it's your wish either to use epsilon or to use epsilon m. Okay, so when you're dividing this either this epsilon or this epsilon m with this epsilon naught, then that gives you epsilon r. Okay, that gives you epsilon r, which is relative permittivity. Very important that we'll be using in many places. Okay, so epsilon r is equal to k, which actually here we have said two k's, right? Here is also k, here is also k, and then here is also a k. Actually, this k is capital K. And in this K is actually not capital K. Yeah, this K is actually small k, but whereas this K is capital K. That means two K's aren't same. For that K, it's actually a constant value. But here it differs for every material, like that K only, but that K is with the formula. Here it is different. Just understand that. Those two are completely different. Just because both are K doesn't mean that they both are same KKs. Okay? So epsilon by epsilon naught is equal to permittivity in any medium whole divided by permittivity in air. So here this is what the definition is. Epsilon means permittivity in any medium and epsilon naught means permittivity in air or in vacuum. So when you are dividing these two terms, automatically it will be giving you epsilon r, which is k. Okay, so here k is a constant. And here it is actually a capital K. Here it is capital K. So if you want to write it in order of formula, I will write it down. So epsilon whole divided by epsilon naught is equal to epsilon r, which is equal to k. Okay, where this k is actually capital K. Okay, so where this k is actually capital K. Yeah, that's it. Very simple. So here it differs. Epsilon r is see here every value will be differing. See, actually this is a constant. This is constant for air. For air, what is the value I have said? Just now we have seen here, right? So it's actually 8.854 into 10 to the power of minus 12 coulomb square meter to the power of minus 2 and Newton to the power of minus 1. That is what for permittivity is in air. Then permittivity for any medium, that means the permittivity in air will be different. Permittivity in water will be different. Permittivity in oil will be different. Permittivity in metals will be different. Okay, so when you're dividing that permittivity with permittivity in air, so that gives you the constant which is K. So here K is actually with these many values. So when this K is in air, that means permittivity in any medium is actually air. When permittivity in any medium is air. So here any medium is air. So air by air is equal to, see, air by air, which is equal to 1, because this and this will be cancelled out. So it's going to be 1. Okay, so we have got here 1 only. Next is epsilon r with metals. So in terms of metals, that means here permittivity. That means the metals will be actually allowing metals will be actually allowing electric fields very easily through them. So that is why it is actually infinite. Okay, so the next is for glass. Whenever this medium is actually glass, any medium is glass, then that will be 5 to 10 around that digit. Okay, because glass density will be different and the glass which you are using will be different. So for all those things, this next is water will be 81 and for mica will be 6. Okay, so it all depends upon this term only. Okay, because this is constant, that is what I have given. Okay, but for every material it will be constant, but when you're taking different materials it will be different. So if you are integrating it or differentiating it, automatically it will be giving you 0 only, because these two terms are constant. Yeah, see, it seems I've written here also. Here also I have written whenever it is an attractive force, okay, so it is an attraction force, so that means it will be actually greater than sorry, it will be lesser than 0. Whenever it is a repulsive force, it will be greater than 0, like that. Here it is. Okay, wow, my handwriting is very good in this. I'm very proud of myself. Okay, so Coulomb's law in vector form. OMG, this vector form is making me nuts. Really, I'm saying. This vector form, this vector quantity, this vectority, this vector addition, vector subtraction, vector multiplication, all these things is in 11th were dead half of me. Really, believe it or not, I was just able to get just pass marks. Okay. So here today in this 12th standard we'll be trying our level best in order to get improved with this vector form. Okay, so what is a vector quantity? Starting from basics I've written here. So what is a vector quantity? Vector quantity is actually a quantity which has both magnitude and in direction. A quantity which has both magnitude and direction, then that is known as vector quantity. Okay, see, modulus will be represented by magnitude will be represented by modulus. Magnitude will be represented by modulus. For an example, let us take that force. Okay, attractive force. For an example, let us take that there are two different charges. Okay, Q1 and in Q2, there is an attractive force. There is a repulsion force between them. Both are positive, or you can keep it as negative. But since I'm a positive person, I'm keeping it as positive. Okay, so there will be some sort of repulsion force. For repulsion force, automatically it will be positive only. Okay, pakka. So here that means let us take that force is going to be 5 Newton. Okay, 5 Newton. Here you have to represent, since force is a vector quantity, you have to represent it with a unit vector here, which is going to be r cap. So here this 5 is the magnitude, which has to be, if you are writing just the magnitude of a vector quantity. See, it is a force, so force values, this is what. So 5 r cap is what the value is. So when you want, so this is totally vector, this is totally considered as vector. This 5 r cap is completely considered as vector quantity. When you want only the magnitude from this vector quantity, you have to put modulus to it. Okay, and when you want the direction, then you have to take this r cap. That is what it means. In class 12 and vector, there is a lesson. Okay, there is a very separate lesson for this. Some I know about this lesson. So yeah. When we are going to that lesson in mathematics, we will be trying our level best. Just now I uploaded the determinants video for mathematics. I will be trying to cover as much as possible. My max sir gave me determinants paper, but I lost in many places unwantedly. Okay, my consciousness was somewhere else. Okay, I have to concentrate in max a lot with sums. Okay, so what is the formula for force? Just now we have seen, right, it is going to be 1 by 4 pi epsilon naught into Q1 and Q2 whole divided by R square. But I don't know why unwantedly I have written everywhere 1 by 4 pi epsilon naught. I could have just gone with just K itself. Okay, so this is for the formula of forces. Just now we have seen it. So now with this force, now you have to get the magnitude. Whenever you are getting magnitude, what did I say? You have to put modulus, then that automatically becomes the magnitude. Okay, so now you want the direction. So for direction, what you have to put? You have to put a cap, or you have to put the arrow mark symbol. So here see arrow mark symbol is there, and here see cap is there. So that means it is going to be the direction. So you have to combine them and write. Actually, this means the vector quantity. Here, sorry. Okay, so this means the vector quantity. Here it doesn't mean the direction. Here, okay, here, see, here whenever you are writing just f modulus, then that means it is the magnitude. Whenever you are writing f and to the top of that f as a superscript, if you are putting an arrow mark, so that means it is a vector quantity, and this vector quantity is having here a magnitude, and here it is having a unit vector. Okay, so that means it is a vector quantity. See, so here I have chosen two. Actually, I should have written it now. I shouldn't have written it then. I feel like I'm wasting some time. Okay, see, this is actually Q1 and this is actually Q2. In that case, if you're taking it. Okay, so this is Q1 and Q2. In YouTube app itself, you're having the ability to zoom in. Okay, so you can just zoom in it and just listen my voice. Okay, so here it is Q1, here it is Q2. Okay, so this Q2 will be applying some force on this Q1. Now we are taking it as an attractive force. Okay, so this Q2 will be applying some force on Q1. So they both will be attracting each other, and in this distance R, which is going to be constant. Okay, pakka, TK, done. Super. So when the force which is given by Q2 on Q1, okay, so this is what giving force on Q1, right? So this force has to be represented as F12, okay, because First, this 1 represents this Q1, 2 represents this Q2. So force on 1, okay, see first you have to write on 1, on which body it is actually, this force is acting on, that one you have to first put. Then secondly you have to put by which body the force is being given. So that means here it is going to be Q2. So this is F1, okay, here it is F2. They both are completely opposite in direction. That means what, from here even we can conclude that F12 is equal to minus of F21. F12 is equal to minus of F21. Their modulus, okay, their magnitudes will be equal. That's it, very simple. Whenever you're taking opposite in direction, that means their magnitude will be equal. Sorry, whenever you're considering of opposite direction, that means their sign will be different. If this is positive, that is going to be negative. If this is not positive, then that is going to be negative. Okay, so here how to do it, I will be just saying it. F12, okay, first you have to put this vector form for this force and this force. So for F12 vector form is going to be 1 by 4 pi epsilon naught into Q1 Q2 whole divided by r square. So here r square is going to be 2 1. See here if it is 1 2, here it will be 2 1. Here also it will be 2 1. If here it is actually 1 2, here it will be 2 1, and here also it will be 2 1, completely opposite. Like that will be F 2 1 will be equal to like this. See here it is 2 1, so here will be 1 2, here also will be 1 2 and leave. Okay, so now you have checked with these two. That is what, from here only I have written it, or the one and only thing that I have done is that I have put some numbers over it. That's it. Okay, so F12, if you just check it out, here R21 and R21 and R12 will be equal. R21 and R12 and R21 will be equal because it is a constant, it is just a distance which cannot be changed. But their vector form will be equal with a minus symbol. If you are putting here minus symbol, then they will be equal. A vector form, when you are taking only the magnitude, here I have to put modulus. Okay, whenever you're taking only the magnitude, then it will be actually equal. So since it is taken only the magnitude, I have just put it like this, which means I've, see here it is 2 1 now. So from this, okay, from this, which is 2 1, in place of 1 2, I have substituted 2 1 because these two are equal. So I have just substituted their values. Okay, that is what I have done. Okay, so then like that itself for r cap also I have substituted the value which has to be 1 2, but instead of 1 2 I have put this value which has a negative symbol. So if it comes before, just take this one, check this one, and then check this one. Okay, these two are equal. That means F21 is equal to minus of F12, like that you can say, or F vector 1 2 is equal to minus of F21. Okay, then next is force in medium. See, force in medium, how big at all, I will not say. From this formula. Okay, where is that formula? Okay, see, from this formula only we have taken it. I want you all to remember one thing. Force in medium, okay? Permittivity in any medium. So what it is going to be? It's going to be permittivity in any medium is represented by epsilon is equal to epsilon r into epsilon naught. So this is what the formula is. Okay, from this formula only I have taken. it. So exactly that is what I'm going to do here. Instead of epsilon naught, what I have done is, see, this is for air. Okay, so this is for air. When it is in medium, this naught has to be taken out. This naught alone has to be taken out. See here, when it is in air, you have to use this formula. But whenever it is in medium, then that means you have to take this naught, you have to remove this naught, and then you have to put this one. Okay, so just the epsilon. What is, just now I've said the formula, right? So whenever it is just epsilon, that means it is going to be epsilon r into epsilon naught. So if you're just considering, see, epsilon r is equal to k. Okay, epsilon r is equal to k, and this epsilon r or k has been taken out from this group. Okay, from this group, just like this, I have abandoned it, and then remaining terms are taken, where remaining terms are equal to this force. So if you just check it out, so that is what I have done. So here force by k, that means whenever objects are being kept in a medium, then that means the force will be retarded. Okay, retardated. So that is what I've given here. So K air is equal to 1, K conductor is equal to infinite, K water is equal to 81, K mica is equal to 6, K glass is equal to 5 to 10. It differs from 5 to 10, it can be anything. Okay, so note. So what is here to be noted? Okay, notice that if a glass slab or a mica is kept between two charges, then the force decreases. Yes. So if here is a charge, so here is a charge and here is a charge, and in between there kept a mica, then automatically the repulsion or their attraction force will be decreased. Okay, it can be glass slab or it can be just mica, it can be anything. Okay, and also the metallic, if a metallic slab is kept between two charges, then the force becomes zero itself. The force completely becomes zero itself, because for that epsilon r value is equal to 1. For metals, epsilon r is equal to 1. So infinite is literally can be termed into 0. So yeah, not in everywhere, some places like this places you can take it as 0. Two charges are kept in different mediums and are having same separation. Okay, so I have two different charges like this. Okay, so q1 and q2, and are kept in different mediums. Okay, so see, this is q1 and then this is q2, which where these two charges are kept in different mediums and are having separate and are having same separation. Actually, it will not be like this. Okay, so here you have to take two cases. Okay, here you have to take two cases. First, what they are coming to say that you have to understand. They are two different charges. Okay, and they are being kept in two different mediums. That means one can be in air and another can be in water. Okay, and are having same separation, and are having same separation in sense. See, case one, which is, okay, so this is in air. Let us keep that this is in air. Okay, so here it is actually q1 charge, here it is actually q2 charge, and then these two are having some distance. So let us take this as r distance. Okay, so this is next I have kept in water. So here in water also, this is q1 charge, same q1 charge, and then q2 charge. This is also same distance, which is r. Okay, so that is what they are saying. Okay, two charges are kept, but they are having same separation. They are having same separation. And then see, here also r, here also r, right? So that is what the same separation is. So when you are inputting the values, at last you will be getting like this and like this. So yeah, this and this will be there. This and this, if you are equating them, the one and only difference between them is that, see, here k2 is there, here k1 is there. Other than that, everything is equal. Okay, so that is why I'm multiplying this f1 with k1 and this f2 with k2. So when you are multiplying this one, here also k1 will be coming, right? Here k2 will be coming, right? So k2 will be cancelled. Here k1 will be cancelled out. So that is why we are multiplying. So after multiplying, they both will be equal. So that is why I have equated them. Okay, then after this, oh god, we are going very fast today. I like it. Okay, see, if two charges are having the same force in different medium and a different separation, okay, so which means here also it will not be like this. Sorry, I've written it wrongly. So case one. Okay, so this is q1, this is q2. These two are having some force. Okay, that force is actually equal here and here. Here also q1, same q1. Here also same q2. Okay, here also they both are equal. Here it is r1, here it is r2. Okay, and here if see, it is in different medium. That means it is actually in air. Here it is in water. Okay, so in that case, what will be different? Here, first of all, this radius will be different. Okay, and then secondly, there will be this k constant will be different. Okay, but here, see, here what will be different? It is very basic thing. Okay, What will be different that you have to write? What will be different that you have to write? Here, what is different? Two charges are kept in different medium. So that means K value will be different. And then also they are having same separation. That means R is same, but whenever this word different medium is there, then you have to come to know that force will be also different. So automatically write in this formula like F1 K1 is equal to F2 K2. Here they are given that it is in a different distance and also it is in actually different medium. So that means in distance in formula is written as square. So r square. That is why here also square, here also square. Like that you can remember it. Okay. Huh. If one medium over there is actually air, like this, okay, like this in air, then that means R2. This distance is equal to R1 whole divided by root over K2. So here if you can consider either K1 or K2 as air. So that means that will be having 1 as its value. Then if you are proceeding, it will be correct. Okay, next is if a glass slab, okay, if a glass slab is placed between two charges with a thickness of T. Okay, a glass slab is there, so that is being placed between two charges, and that is actually having thickness of T. So that means this distance, okay, first is this is with this R distance, then it has become into R dash distance. Okay, so this R dash is equal to R minus T plus T root over K. That means this new distance is what this is. Okay, the new distance is R minus T plus T root over K is what the new distance is. So force is equal to 1 by 4 pi epsilon naught into R by Q1 by Q2 whole divided by the new distance has to be put in square. So R minus T plus T root over K the whole square, like that you have to put. Okay, so what are the points that you have to remember is that this Coulomb's law is not applicable for everything. Okay, Coulomb's law is applicable when and only to point charges, and then the distance between these two charges must be more than 10 to the power of minus 15 meters. And then the third is that it is actually Newton's third law. Yeah, it is actually following Newton's third law. One of the most important point, but which I have forgot to say, that is this is actually, okay, see here minus is there, so every action has its own opposite and equivalent reaction is Newton's third law. So this Coulomb's law is following Newton's third law. Next is superposition. What is superposition? That means a lot of charges are being kept around it, around a charge. Okay, so here this is what that one charge is. See, a lot of charges are kept around one particular charge. Okay, so this charge will, all these charges will be opposite in sign with this charge. Okay, if this is negative, these all will be positive. If these all are positive, this will be negative. Mostly. Okay, or also all of them can be positive or all of them can be negative. I've said every case, but mostly they will be opposite in sign only. So F net is equal to F1 plus F2. See, it will be having one force, 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 right? So totally you have to add their forces. That's it. Okay, you have to add their forces. So here you have to use vector addition. Here you have to use vector addition. That's it. Okay, so charge, okay, so densities slash continuous charge distribution. So actually what it is, okay, so density slash continuous charge distribution is actually, see, density is actually of three different types. Sorry. Okay, see, density is actually three different types. First of all, it's going to be a linear density, then second is surface density, then third is volume charge density. So for linear density, what it means is, see, you have to take a linear thin line, okay, or a thin wire. So the charge density that is with this particular wire is there, right? So that is what we will be saying as linear charge density. So surface charge density means you have to take a two-dimensional object. Here you have to take a one-dimensional object. Okay, here you have to take two-dimensional object, and then the charge density that is with this particular object is what known as surface charge density. Okay. Next is for volumetric charge density. It is actually you have to take a three-dimensional object, and then the charge that is with this three-dimensional object is what actually known as charge density for this one. Okay, Paka. So what is actually density here? Actually, these densities are represented with three different signs. For linear charge density, it will be lambda. For surface charge density, it will be sigma. For volumetric charge density, it will be rho. Perfect. So here, first of all, what we have to do is see. So here it is there. So you have to actually bring a particular unit charge. Okay, not a particular. You have to bring a unit positive charge from P point. Okay, from some point 2 towards that particular object. So here it is actually a wire, right? So first, what is this density? Density has to be divided with its particular dimension. So here it is actually length is the dimension. So charge by length. Okay. So here it will be area by length. For volumetric, it will be volume by length. So that is what. Okay. So here I have taken only one small point. If you just know that here, this one small cross section we have taken here. Okay. So that means the charge will be also very small. That is why I have represented here with dq by dl. Okay. Paka, super amazing. So if I bring this to over here, so that be lambda dl by dq. So with this force, we have this formula which is d naught into dq. Okay, so with this dq is actually one charge, and here this total this dq represents this total wire, and this d naught represents this particular unit positive charge. Okay, so now I'm integrating them because of this d. So if I integrate it at first of all, we have to take only the constant outside of this integration symbol. So 1 by 4 pi epsilon naught is a constant, also q naught is a constant, so this will be staying inside itself. So dq can be written as, see, dq is equal to lambda dl, right? So which means here dq can be written as d lambda dl whole divided by r square naught. Okay, here r square naught is the distance between this unit positive charge and this wire. Okay, okay, done. Okay, surface charge density is same like that only. So like that if you're taking, and here at last this will be the formula for surface charge density, and then for volumetric charge density this will be the final formula. That's it. Okay. Okay, wow. Okay, we have completed this one video successfully, very fastly. If you are feeling that you are having some trouble with my English, well, I'm very sorry. I will try to reduce the fastness of the English next time. Okay, so thank you. We'll be meeting in another amazing video. I hope you like it. And if you're having some doubts, you can just ask me in the comments, no matter what doubt it is.